Good morning everybody. So, in this chapter we will be talking about our coordination compounds. And again there will be 6 classes. So, today we will basically introduce what we basically know about the different coordination compounds and the name basically about this coordination compound, because all we know that there are chemical compounds as well. So, like that of our sodium chloride, magnesium chloride, all we know that they are typically metal salts, and at the same time we can consider them as inorganic compounds. So, this is one example of an inorganic compound of sodium ion, and second one is also an inorganic compound of magnesium ion. But what else to be there which can define another group of compounds which we will be calling as the coordinate compound or the coordination compounds or the complexes. So, in coordination compounds we will have a typical coordinate bond. Here in this class of compounds, what we see that they are having ions Na plus Cl minus, and at the same time magnesium 2 plus and 2 Cl minus. So, they are packed in the lattices. So, they are forming some ionic bonds, and these are ionic compounds. And compared to that, if a particular compound having some coordinate bond, and coordinate bonds all we know that is particular bond is also known as a dative bond through some donation of electron charge. So, very simple molecule what we can consider to our life from the very existence of our life also, and anywhere we know that this water molecule, simple water molecule, and the covalent structure, that means is a covalent molecule we all know, and only there is partial charge separation, as we all know that this is delta plus, this is delta minus, and this is also delta plus, and this is also delta minus. So, basically what we find that dipoles are created along this OH bond, and another one is also along this OH bond. Now, if this lone pair of electron can be utilized for some bonding interaction to any species like say any metal ion. So, it is a particular donation, unlike that of sharing or the ionic compound formation. Here we have the two lone pair of electrons forming a bond between O and M, that means we can have a OM bond. So, what we are considering over here is a typical OM bond. So, OM bond, if that particular OM bond is a coordinate bond or a dative bond, where the lone pair of electrons utilized for the formation of that particular OM bond is coming from the oxygen atom of the water molecule. So, this oxygen is from the water. So, this is coming from the typical water molecule. So, then if we can have at least one such interaction with that particular metal center or the metal ion center, it can be a transition metal ion or a non-transition metal ion as well. So, we can consider that we are just leading towards something where we are able to get some coordinate compounds or coordination compounds. So, that is there if we can see where we are able to develop a particular chapter which is devoted to coordination compounds, and it is typically a backbone or spine or is the main thing for modern inorganic chemistry. So, the latest one, because it is typically developed during the last 100 and 120 years. So, this particular development is say for 120 years following Alfred Werner. So, Alfred Werner So, Alfred Werner studied all these compounds during 1890s. So, and that particular type. So, during this last period, that means we get the period where we can isolate the elements before that. Then when we identified, that means the discovery of the elements, we discovered the elements, and afterwards we can put them in the periodic table, their positions and their electronic configuration, structures and everything we studied in detail. But this particular concept during the last 120 years has been so useful that the modern days coordination chemistry is basically devoted to typical inorganic chemistry also. So, any inorganic compound, if we just consider that we have a simple metal salt, M is there having a charge of Mn plus, and that is a typical salt. So, what type of salt? We know that the from earth crust we get something as the oxide, hydroxide or carbonate or sulphide, ores and minerals. So, ores and minerals, when we treat it with some mineral acid, so acids are given and those acids are providing the corresponding anions. So, these are the anions which are coming from the acids during the treatment of these ore and minerals for isolating a typical metal salt, say nickel sulphate, say iron sulphate or copper sulphate if we want to make, because the copper will be present as copper 2 plus and the corresponding anion will be present as the corresponding anionic salt. But once we make that particular salt, as I told you earlier, that we can go for the corresponding solution, that means we put that particular salt in water. So, we are putting that metal ion within water. So, all these informations and all these understandings can be there how our Mn plus will be staying inside these water molecules in the solid state as well as in the solution state, and sometimes if these salts in terms of the corresponding anions as isolated as the hydrates, that means dot NH2O. So, if we isolate them as the hydrates, so this how these water molecules are interacting with these salts as well as the corresponding metal cations also. So, this is also the very important thing, that means the very backbone of our bioinorganic chemistry. That means this particular thing, that means the biologically if we have say iron, we all know that iron in a particular oxidation state, it is there in our blood. Where it is present? It is present in our hemoglobin or it is present in our myoglobin. So, the presence of this iron in form of a coordination compounds is also there in biology. So, that we will see that how useful they are in studying the presence of iron as coordination compound in some biological species. And it is also very useful in different chemical industry, because chemical industry all we know that is very much dependent on the presence and usefulness of some good catalysts. So, catalysts will be there, and those catalysts if they form some coordination compounds, they can also be useful. So, different types of organic transformations, the industrial chemistry is not only devoted to inorganic industrial chemistry, but it can be for organic industrial chemistry, the medicinal industrial chemistry or the pharmaceutical industrial chemistry, where you simply use some of these important coordination compounds. Say one important thing is that hydrogenation. We all know that hydrogenation process can be utilized or can be done utilizing some Raney nickel type of thing, where the nickel is present as nickel 0 and it is activating the hydrogen gas and that can be hydrogenated. So, what we see here that instead of that nickel as nickel 0, we can have some nickel complex or any other metal ion complex which can also be useful some useful for some specific hydrogenation reactions. So, these compounds, that means the coordination compounds, will be useful for chemical industry as well. Then also we see that how these can be utilized for the different pigments. This is also an application part. So, Prussian blue all we know, and the aureolane is also another compound, and the alizarin red dye. These are the three examples, again have been taken from your CBSE book. So, everything is there. So, what is this Prussian blue? Definitely this color is highly intense, and that Prussian blue can be utilized as paint. But why this is colored? Because of the when we study everything, but this particular formulation, because once we know the compound and its color and its usefulness, then only we can immediately say what should be your corresponding formula. This is KFe, Fe, FeCN whole 6. So, what is that? Well, this particular part, that means some part we are writing in square bracket, which is FeCN whole 6. So, nature of that particular thing we just try to find out. Similarly, another yellow compound, yellow pigment which will be there, which is aureolane, which is also a cobalt compound. And in this particular cobalt compound, what we see that this is NO2. This is NO2, that means nitrite ion is there. So, nitrite can function as a ligand around cobalt. So, typically what I just told you, that if you have the corresponding anions which are coming from the mineral acids, you get the simple sorts that of your ferric chloride, nickel chloride or copper chloride as cupric chloride. So, chloride anions are coming from the corresponding mineral acid, which is hydrochloric acid. But if the corresponding anions are different, here it is Cn minus, the cyanide ion, here it is NO2 minus, the nitrite ion, still we get some coloration for the presence of those anions as well as the corresponding central metal ion. But these are not very simple or the corresponding simplest possible example what we know for the corresponding metal salts. These are not metal salt. Here we have written in square bracket, here also we have written some part in square bracket, and afterwards we will see what is that interpretation for writing these in terms of the corresponding square brackets. We will find why they are so colored and how they are utilized for the pigment. Another example is an alizarin red dye, which is nothing but an compound of anthraquinone. But the example of this red dye is telling us that we have something, that means it is not the typical 1,2-dihydroxy 9,10 anthraquinone. We all know anthracene, we all know quinone. So, it is anthracene based quinone. Okay. So, and its 1 and 2 positions are also hydroxide groups. So, these hydroxide oxygen and this anthraquinone oxygen can be utilized for the formation of the coordinate bond to what? To the aluminum, aluminum as aluminum 3 plus. So, red lake or red dye is a brilliant red coloration is only formed when it is forming a coordinate compound or a coordination compound to aluminum only. So, this can be utilized as again a red pigment. So, these are the typical example, one is blue, another is yellow and another is red. So, these three useful colors we occasionally use all of them the way I have told you earlier, that means the lead chromate how we can use in painting school buses. So, this is some red dye, but the red dye is only obtained when we utilize this aluminum, and aluminum is forming some coordinate compound with this. So, we will define this 1,2-dihydroxy 9,10 anthraquinone as something where the oxygen atoms like our water molecules having lone pair of electrons can form bonds to the aluminum center. And this is one more good example that we should not confuse ourselves, that all the coordination compounds are forming from only the transition metal ions, that means the 3D, 4D and 5D elements. It can be with other metal ions where you have filled d orbitals like zinc, cadmium and mercury. Similarly, it can be with magnesium, it can be with calcium and it can be with aluminum also. So, alizarin red dye which is forming something, that means the calcium, you can have the calcium dye, you can have the aluminum with the aluminum dye. So, bound metal ions are important, that means these are all present in the anionic form. The cyanide is present as the anionic form, that means the cyanide ion. Nitrite is formed as the nitrite ion. Similarly, this anthraquinone, hydroxyanthraquinone, if they go for deprotonation and hydroxy groups are present as O minus of the phenol unit, then it can bind either calcium or aluminum or both of them together to give some a red dye compound. So, the coloration again is due to the formation of this coordination compound. So, what we come to know from here is that the usefulness of this coordination compound, where the different color we can generate due to the presence of these metal ions, which is forming a coordinate compound or a complex species. What is that? Because these metal atoms are ions. So, here iron, cobalt, calcium, aluminum, all of them are present as metal ions, but in some other cases also we will see that we can have the metal atoms also, like nickel 0. The nickel 0, as just now we are discussing about our Rani nickel, where the nickel as the fine powder having a very small size, those are nickel atoms. But those nickel atoms, if it interact with some other species like carbon monoxide, we all know that nickel can form very good compound, where the nickel 0 in 0 oxidation state can bind to 4 carbon monoxide molecules. So, carbon monoxide molecules are gaseous compounds. So, the gas is bound to the metal center, where the metal is in the 0 oxidation state, but due to this thing, that means due to this definition, the metal atoms, that means the nickel atoms, are bound to a number of neutral molecules. Here the carbon monoxide is the neutral molecule. So, that species which is forming out of nickel 0 and the carbon monoxide is also termed as a coordination compound. So, it is not that the metal ions like iron in Fe3 plus or cobalt in cobalt 3 plus or calcium in 2 plus or aluminum in 2 plus, but the metal in the 0 oxidation state as metal atoms can give rise to the coordination compounds. And in the biology, that means in bioinorganic chemistry, what we study is basically, we all know the typical names from our school days. What is chlorophyll? We all know, we can define, we can say the function, we can show its reactivity. Similarly, just now I told you about the hemoglobin and the vitamin B12. Why they are important in terms of the coordination compound? Because they are again a chlorophyll by definition is also a coordination compound. Hemoglobin as well as myoglobin, which is present in our blood, is also by definition a coordination compound. Similarly, vitamin B12 is also a very interesting coordination compound, where cobalt is present, and not only a naturally occurring bioinorganic coordination compound, but is also having some metal carbon bond is giving. So, it is a bioorganometallic compound also. So, B12 is a vitamin B12 is also a bioorganometallic compound of cobalt. So, you have magnesium. So, if somebody asks you to identify the metal ions present, so chlorophyll will be having magnesium, hemoglobin or myoglobin will have iron, and then vitamin B12 will have cobalt. So, we see that the typical definition, a standard textbook definition, we should always keep in our mind, like knowing the periodic table. What is then your coordination compounds? So, it basically contains one or more complex ions, which is very important. So, afterwards we will define also, like just now we have seen that we can write a compound like K3 FeCN whole 6, and from our school days we all know this is potassium ferricyanide, where iron is present in +3 oxidation state. So, this potassium ferricyanide, so this is the part which we write in square bracket is the complex part. So, this is again a compound. So, this is again a coordination compound. It has a complex part. So, this part on the right hand side we have a complex part. So, complex part is anionic, and the charge is balanced by the simple potassium ion, because the whole charge on this complex species is 3 minus. So, for potassium ferricyanide you require 3 of the potassium ions to balance this particular charge. the way we write, we all know that the aluminum trichloride, aluminum has a tripositive charge. For charge neutralization, we require 3 such chloride ions to balance it. Similarly, this anionic coordination compound is trianionic. So, we require 3 potassium ions to neutralize its charge. Overall, this coordination compound is a neutral one. So, is a neutral coordination compound. And sometimes we will also see that this particular part, that means the cationic part, can also be a complex part. Similarly, the anionic part can also be a cationic part, complex part. So, these two parts, so this is complex and this is also complex, and together these two we call them as your coordination compounds. So, that tells us that one or more complex ions, which is important, one or more complex ions, where we have the more complex ions, that means at some time we can have both the cationic part as complex entity and the anionic part is also a complex entity, where we find that a small number of molecules or ions surround a central metal atom or ion. Just now the examples what we are looking for is that a small number of molecules. So, these what are those small number of molecules? That means it can be your water molecules or it can be your cyanide ions. So, small number of those molecules or ions surround a central metal atom or ion, usually of the transition metal family. It can be usually 3D, 4D or 5D metals, but it can beyond those transition metal ions. So, in a typical form, either it can have the atom like nickel tetracarbonyl NiCO whole 4, we will just discuss afterwards in detail, or you can have K3FeCN whole 6, where the cation is bound to some anions, we get the coordination compounds. And these coordination compounds also by definition, they are very useful depending upon the number of groups, the small groups, number of small groups attaching to the central metal atom or ion, we get different coordination geometries. So, that we will just elaborate also. These are the typical definitions, how we define a coordination compounds, and we will be able to get a corresponding linear, tetrahedral, square planar or octahedral geometry. So, versatility is very high apart from your typical organic chemistry, where we know that the carbon center we have restricted geometries, carbon can be planar, carbon can be tetrahedral, not beyond that. But here we see that from a linear arrangement to a octahedral arrangement, a metal ion, a specific metal ion can extend its geometry during the formation of your coordination compounds. And not only our application in modern day inorganic chemistry, bioinorganic chemistry or industrial catalysis, it has also some application in electroplating. If we go for fine plating on some surface, textile dyeing, just now we have seen the corresponding dye for based on calcium or aluminum, and in the medicinal chemistry some of these metal complexes or the metal compounds are very good as the pharmaceutical history, like our cisplatin, which is a platinum based anti-cancer drug. So, when we go for these, that means when we go for this processing, we use a variety of metallurgical processes also. That means the identification or the isolation of silver, isolation of gold. We use the cyanide as the typical process. The cyanide process is basically based on the corresponding formation of the coordination entity or the coordination species in solution. Then just now we discussed the industrial catalyst and some analytical reagents. So, just now what we have discussed about that corresponding dye, which is for giving you color to your calcium or aluminum. So, that can function as a very good reagent. If that particular compound, the anthraquinone, the 1,2-dihydroxy anthraquinone compound, if itself is not so strongly colored, in the anionic form, when it is bound to aluminum or calcium, we find that the color intensity is increasing and we get basically red dye. Dye is all are very colored, very much colored, is a pigment what you use as a pigment or the dye. The intensity for those colors are very high. So, what we can utilize it because it is not we will not be able to discuss all these in detail. So, this is the right time where we can say you about this analytical reagent. So, that particular reagent, that anthraquinone, dihydroxyanthraquinone can function as a very good analytical reagent to detect the presence of calcium ion or the aluminum ion in any unknown solution, because the calcium ion or the aluminum ion, when it is present in aqueous solution or water medium, it is colorless. As we put the reagent, that reagent will develop some beautiful that red lake. Usually we go for the in the corresponding semi micro quantitative analysis, even a spot plate. The spot plate analysis is also very useful. So, in a drop of those reagent can give rise to some beautiful coloration or the lake formation for identification, because you can have the shades of those two colors, because when both of them are present together it has a different color. When only aluminum is present it has another color, or when calcium is present, though they are very close by, but we can identify those coloration by knowing the thing, the color, that what particular coordination compound it is forming. So, in this particular analysis. So, analytical chemistry finds is typical application during the formation of these coordination compounds. So, we will now take the example of some compound which we all know from your laboratory classes also, which is our Morse salt. So, this Morse salt, we consider it as a salt, and we are asking ourselves whether we can label it as a coordination compound, whether some coordinate bond is forming over there, and when it is Morse salt we tag, we definitely know that it is a ferrous compound of iron. So, Morse salt iron is present. So, there will be some small molecules or anions present also along with that, and whether that particular anion or small molecules forming some coordinate bond to the iron center or not, that will define whether your Morse salt is a coordination compound or not. And analytically also we find that this Morse salt, which is ferrous sulphate, ammonium sulphate, 6 water molecules. So, the name of this compound is ferrous ammonium sulphate, or it is a double salt of ferrous sulphate and ammonium sulphate along with 6 water molecules of crystallization. So, it separate out or it crystallize out from the medium nicely as this formulation. Center dot is given. So, that is why these are all packed in the crystal lattice. So, there is no such interaction with the iron center with that of your ammonia or the ammonium ion. So, we should be very much careful that no such coordination of ammonia as ammonium ion or ammonia as NH3 is to that of your iron center. Similarly, another example is that your potassium alum or potass alum we call, so which is potassium aluminum double salt. So, it is the potassium sulphate as well as aluminum sulphate double salt. So, double salts are two salts together, they co-crystallize. So, it is a co-crystallization process, and in a single entity they are crystallized out, and they have the typical identity that when they dissolve it in water, it can dissociate into the simpler ions. So, when we dissolve potassium salt of this, that means the potassium alum or the Morse salt, what we get? The Morse salt, already I told you that this Morse salt we have Fe2 plus in the system. Similarly, in solution, whether this coordinate bond is present between iron. So, what we are expecting, this ammonium ion we are expecting, that means whether we can have a typical interaction like this, or when you dissolve it this can form or not. So, this can be derived from your ammonium ion. So, water can sometime be very useful to get this, whether this is forming over there, and the resulting some complex entity or the complex species is there, which will not dissociate altogether in the medium as Fe as Fe2 plus or ammonia as the neutral ammonia molecule or ammonium ion. But in actual practice, when Morse salt is dissolved in water, we are able to detect the presence of all the cations and all the anions what is present over there in the salt, ammonium ion and the sulphate ion and large number of water molecules. So, we will be able to detect the ferrous ion, we will be able to detect sulphate ion, we will be able to detect ammonium ion, not that we will be getting something where we have the corresponding presence of these ammonia as this ammonium ion or some complex species. So, no complex species is there. Ammonium ion is also present as ammonium ion, which can be detected over here as ammonium ion. So, it is not a coordination compound, it is typical an example of a double salt. So, more salt like these salts are all double salt. So, we will not get that. But just now what we have told you that we are having potassium ferricyanide. Now, then another example is potassium ferrocyanide, which is instead of K3 it is now K4 FeCN6. But this particular species, if we take and if we try to dissolve it in water, we will not able to detect the presence of ferrous ion, but the salt is of ferrous. We will not be able to detect ferrous ion in the medium or the cyanide ion in the medium, which is also highly poisonous. So, this particular part which is written in square bracket, nowhere here we have written anything in square bracket. So, this part which under this square bracket thing, we get that this particular entity due to the formation or due to the reaction or due to the bonding between iron and cyanide, iron as ferrous and the cyanide ion forming a coordinate bond, giving a typical entity or a separate entity whose nature is completely different, which is the corresponding ferrocyanide anion. So, ferrocyanide anion is the corresponding complex species. So, we will able to generate something which is a complex compound. So, this is some typical example. So, this is the anionic part which is complex one. Similarly, when we get this one which is the cationic part, which is 6 ammonia molecules are bound to the cobalt center, which is the cationic complex species. Here that is the example where we are saying that both cationic part as well as the anionic part are the complex species, but we get the corresponding coordination compound where the copper part is the cationic part and the platinum part is the anionic part. Similarly, this compound that the medicinal value just now I told you can be your cis variety, where two of these groups, that means the same groups, that means the nitrogen from the ammonia are 90 degree to each other, as we know in the definition for in the organic chemistry, the cis definition and the trans definition. If this particular coordination compound has a geometry of a square plane. So, if the cis variety is the corresponding medicine which is known as cisplatin, but the trans variety is not. So, isomerism will also tell us or dictate us the very usefulness of those compounds, but here also we see the 3 examples. This is the cationic example of the complex part, this both cationic and anionic, and this is the neutral part for this corresponding compound. So, we should always be very much careful the nature of these compounds. So, nature of these compounds, how we identify those natures. So, these are typically the different salts. So, when we dissolve it in solution or water, we find that this can be separated as the cationic part and these are the anions as 3 chloride ions. So, we can detect the number of chlorides you can get from this particular salt. Similarly, here we are not able to get any chloride from these compounds, whether it is present in the cationic part or the anionic part, and obviously it is present in the corresponding anionic part, but this chloride you cannot take out. So, this has a typical example for the reactivity pattern or the reaction pattern if we try to immediately detect the presence of chloride. Similarly, this will also behave differently. So, all 3 compounds, if we try to treat it with a dilute solution of silver nitrate, which we all know that silver nitrate is the reagent where you can detect the presence of chloride ion in sodium chloride, say in aqueous solution. So, if a aqueous solution of silver nitrate is also added, we get the precipitation which is very sparingly soluble, or also sometimes we say is insoluble if the volume of the medium or volume of the reaction is very less. So, in small volume medium is basically getting precipitated, and silver as the precipitation of silver as the silver chloride, which is a white compound, and you can able to detect this as the presence of the chloride in the salt as the chloride as the anion. So, similarly the hexaamine cobalt 3 chloride, when we see the systematic nomenclature also, it is the name of these, the naming also we should know how you name it. Okay. So, this is hexaamine. So, amines are the ligands, we will also define what are those ligands. So, hexaamine cobalt 3 chloride, when we react with silver nitrate, it will also give rise to 3 AgCl molecules. So, 3 AgCl. So, amount of AgCl we can take out, we can filter it out, we can take the weight of those, and we can say that the quantitatively all the chlorides can be removed from this medium. That means, chlorides are not bound to the metal center. So, the chloride ions, if we consider them the species which is bound to the metal center, as by definition we will define them as the ligands. Why we call them ligand, that we will also will see. So, in this particular case the chlorides are not ligands, but here these are ligands, here also these are ligands. So, we cannot eliminate chloride as silver chloride from these two compounds. The way we are seeing the corresponding taste of ferrous ion or the corresponding taste of cyanide ion is missing in the ferrocyanide or the ferricyanide ions. Okay. So, the analytical chemistry is always very much helpful, and the physical measurements also, the physicochemical measurements also will also be helpful, because we all know in the physical chemistry classes that these ions are very much helpful for giving you as the corresponding conductivity. So, the corresponding molar conductivity is also will be different if we just consider that this chloride is dissociating out and is found freely in the solution to conduct electricity, or these chlorides are very strongly bound to the metal center and not available for electrical charge conductance. Okay. So, it is that person what I was just telling in our first slide, that it is Alfred Werner. Alfred Werner during 1866 to 1919. So, during 1890s basically he proposed this concept, and he basically brought at this particular time that we are only basically at the beginning of this PM, when nothing is known about the nature of the electron, the proton, neutron and all these things, that the nature of these two valence, one is primary valence and another is the secondary valence of the metal ion. So, what we just see that instead of cobalt chloride as the salt, we all know the cobaltic chloride would be COCl3. So, now what happens if we add some amount of ammonia to that cobaltic chloride. So, cobaltic chloride is the typical inorganic salt. So, like all other metal salt, so cobalt chloride, so cobaltic chloride if we can have, so C should be always capital. So, COCl3 is the corresponding salt of cobaltic chloride, where we know the cobalt is present as the 3 plus and the chlorides are as Cl minus. Then we bring something like water molecules, sometimes we can also use water. So, these are the species which can interact with the metal center and give rise to the complex species. So, the formula what we get this particular salt is there intact, but these ammonias are also strongly bound, not only a single ammonia, but several ammonia will be bound to this particular species. That means, this ammonia molecules will be some entity which is directly attached to this cobalt center, and if like that of our water, water having the lone pair of electron, this ammonia also will have some lone pair of electron, and if this lone pair of electron can be donated to our cobalt center, the cobaltic center, the trivalent cobalt center, we get some species belongs to that corresponding coordination compounds. So, the primary valence will be there, the charge neutralization, and the secondary valence of the metal ion will be talking about when we have the complex species. Okay. So, these two things we are having. So, we can have several compounds like this, that means the cobaltic chloride we take and we react with ammonia, and if we try to crystallize it. So, initially we get different solutions. The first, how we can identify them, because all these transition metal ions, the most important property of all these transition metal ions will be utilized for this purpose also, and is also very much useful is the corresponding formation of the different colors. So, when cobalt 3 chloride is reacting with ammonia, and if we consider that in a different stoichiometry or in different reaction condition, the number of ammonia molecules reacting with this cobalt 3 chloride can be different, and depending upon the nature of this color, that means we can have different colors. So, this cobalt and these compounds with you have the N, that means the N, the way we say that the order of crystallizations, these are not crystallization, these are the molecules responsible for coordination to the central metal ion. So, if the N number is varying, so different number of ammonia molecules attached to this cobalt chloride will be separated out from the medium. So, what we get? We get something, that means the complex ion species, where these complex ion species are made up of this cobalt and ammonia. So, it is forming due to the presence of this cobalt and ammonia, and these chlorides can be outside our coordinate sphere, we will call them, and depending upon the different number again, that means it can also be x. It can be 3, it can be 2, it can be 1, or it can be 0 also. So, initially visually we can check these as the different colors. So, color reactions will be different as the stoichiometry is changing, because you are having different complex species forming in the reaction medium. So, we see that when we try to do the reverse one, that means the way we are identifying the chlorides, the number of chlorides, whether we can able to detect it by use of silver nitrate. So, the product of this reaction of cobalt 3 chloride with ammonia, the presence of chlorides can be detected by the reaction of silver nitrate in excess in solution. We will see that the sum of the chlorides can be precipitated out as silver chloride, others are not. So, what are coming out as silver chloride? Those are the typical anionic chlorides which are present as the salt in cobalt chloride. Those can be taken out by the reaction of silver nitrate as silver chloride, but other chlorides which are bound to the cobalt center cannot be taken out. So, those cannot be separated out by the use of silver nitrate for the precipitation of silver chloride from the reaction medium, because this interaction with the silver ion, that means Ag plus reacting with Cl minus, giving rise to insoluble silver chloride, is the ionic reaction, and that ionic reaction is only giving rise to the presence of only chloride ion, and due to this very low solubility, that means the corresponding value of the solubility product is very less. So, the solubility is also very less in water medium. So, they separate out as insoluble species. So, this silver as silver chloride will be separated out, but it is not possible if that chloride is directly attached to that cobalt center. So, first what we get is a yellow compound. So, very useful compound, yellow compound, and this particular stoichiometry what we get yellow, and sometimes depending upon the nature of the crystals, it is a little bit of oranges also. So, this is orange yellow in color, or sometimes typically orange in color, depending upon the size of those crystals what is forming. So, is a yellow coordination compounds. As we go for a reaction of cobalt 3 chloride with ammonia, so and the stoichiometry of these, because we all know that the typical stoichiometry is there, because the reaction is with one of these and 6 of these ammonia. So, 1:6 reaction product is giving us COCl3.6 H2O. So, we are not elaborating it like this, we are taking the presence of these ammonia molecules as the corresponding presence as the corresponding solvent of crystallizations. Ammonia is also the ammonia in the liquid form. So, it is present in the corresponding species as the corresponding solvates. So, if it is ammonia solvates, then it is fine. So, this compound, if we analyze it also for the percentage of cobalt, percentage of nitrogen, and percentage of chlorine also as chloride, we will find that this is the corresponding typical molecular formula. So, that typical molecular formula also corresponds to the corresponding this reaction what we just now told you, that if the product of this, that means the yellow compound, dissolve it in water and react with some colorless and solution of silver nitrate. So, silver nitrate in excess, because we put excess silver nitrate such that all the chlorides which are present over here can be removed. So, 3 of these chlorides which are present in cobalt chloride as COCl3 can be removed by reaction with Ag plus as AgCl3, AgCl as 3 chlorides of 3 molecules of AgCl. So, what we find that all the chlorides present in cobalt chloride as the corresponding metal salt can be removed. So, these chlorides are not taking part into the corresponding valence which is utilized for the direct cobalt chlorine bond for the complex species formation. Similarly, the next compound we will get is the purple compound, where instead of 3 mole of AgCl we will be getting 2 mole of AgCl, and the stoichiometry is little bit different, of 1 less ammonia we can have with the same COCl3. And the third one is the green compound, where we get or we will be able to remove 1 mole of silver chloride. So, here stoichiometry is again from 6 to 5 to 4 is down, and there is another violet compound. So, these two are pretty confusing to us right now, having the same molecular formula, but the colors are different, one is green, another is violet. So, this basically gives us some important idea that these two compounds, the basic form of the corresponding complex part, that means the coordination entity or the complex entity is same, having 1 chloride outside the coordination sphere. And then another possibility we will also discuss, that we are not able to detect any removal of silver chloride from the compound, which is another category of compound which will be COCl3 3NH3. So, that is another possibility what we can have, and that is the possibility where all of them are attached to cobalt and we are not able to get back any silver chloride precipitation from the reaction of silver nitrate. So, this is again a good thing, which is the table which is taken from your textbook, NCERT textbook, which will again explain the presence of these, that means why we are getting yellow compound, why we are getting purple compound, why we are getting that green compound and the violet compound. So, this formula what we just now we have seen, these were the molecular formulas. So, if we can think of the corresponding molecular formula of these as 6NH3, 5NH3, 4NH3 in 2 different cases, we will find that these can be present over here. In the first case, all the 3, that means all 3 chloride ions will be present over there as the corresponding anions in the typical salt. So, our formula of this compound is CONH3 whole 6 Cl3. That means, we have all the 6 ammonia is attached to this particular cobalt. So, we can assemble, we can cover it. So, in a typical form we can cover by all these ammonia. So, this is ammonia, this is ammonia, this is ammonia, so how we know that? So, we will have all of them, that means all 6 of the bonds, basically 6 cobalt nitrogen bonds. So, we will have 6 cobalt nitrogen bonds, and obviously, this is forming due to the donation of this ammonia lone pair to the cobalt orbitals. And these bonds are what type of bonds? These are coordinate bonds. So, if we are able to detect or if we are able to identify those coordinate bonds, the first category of compound will be these, and these chlorides like that of or any other salt like aluminum chloride. The typical example of aluminum chloride is that when you dissolve it in water, it can dissociate all the chloride ions, and you can remove them by addition of silver as silver ion for the formation of 3 silver chloride precipitate. 3 moles of silver chloride will precipitate out. Similarly, here also you get 3 silver chloride. So, these will be there. So, 6 CON coordinate bonds are there, and what about the cobalt chloride bond if we just consider? So, there is no cobalt chloride bond. This chloride will be outside the coordination sphere. So, no cobalt chloride bond. So, these are the two statements which are very useful and which are very immediately we should all know. So, this is the first compound what is there. The second compound, which this is the yellow compound. So, this is the second compound is the purple compound, and the difference is only thing that you now just change or manipulate the corresponding coordination environment. So, what we do with the second compound, if we write down the formula, because everything is there in your textbook, only you sit comfortably and write the corresponding form. So, here you have 1 Cl and this NH3 is 5 in number and 2 of them are outside. So, think of the corresponding oxidation state. We should not forget the corresponding oxidation state is the trivalent one, and the number of these. So, one of these bond, that means one of these cobalt ammonia bond will not be there. So, we will have 5 of them are nitrogens. So, these 5 of them are nitrogens of the ammonia, and one of them is basically your chloride. So, this is the compound. So, that compound immediately tells us that if you have a charge of 3, one will be balanced. So, overall charge of this complex species, what we write entire thing is in the square bracket. So, entire thing we write basically in square bracket. So, if this is we write, so this charge basically sometimes we write this small squared part to indicate the charge, because the way we write that chloride as Cl minus, Fe as 2 plus, because the species is very small. But when you write a huge species like this and you require some separation, and then we write, so plus 3 minus 1, so it is 2 plus. So, what will be there? So, you will have these two. So, the charge balance will be therefore due to the presence of 2 Cl minus. So, that is why you have 2 Cl minus. So, in terms of these cobalt nitrogen and cobalt chlorine bonds, now you can write it down nicely that we will have 5 of the first category and 1 of the second category. And when we go for the corresponding separation, these two can only be separated, these two chlorides can be separated as silver chloride. So, we will have 2 AgCl from the medium, this will remain as the corresponding entity. So, the third one, we are taking everything from your book, these examples are there in the book. So, the third variety is your green variety, and the green variety we are moving one step forward, where we have 2 Cl bound to cobalt center. So, now you have the third one where you have CO Cl2, and obviously, when 2 of the positions are occupied by these groups, when 2 of them are occupied by these, so obviously we will have 4 remaining ammonia. So, sorry, this is ammonia. So, 4 remaining ammonia groups are there, and that is why the stoichiometry of all these products, in one case we have seen that the stoichiometry for ammonia was 6, the next one it is 5, and the third case it is 4. So, what basically we try to understand over here is that the number of cobalt chlorine bonds are increasing. So, the overall charge of this particular species 2 and 3. So, it is 1 minus. So, outside you will have 1 chloride only, and that chloride basically we can take it out. So, we can take it out as the corresponding one as the reaction of these with Ag plus. So, we will get 1 AgCl. So, that clearly differentiate depending upon the number of AgCl coming out, number of moles of AgCl coming out from the reaction in water medium. So, is all of them are, we are lucky enough to see that all of these compounds are water soluble. So, these things are there, and the ammonia solution what we are using for the preparation are very dilute solutions, because this ammonia, we know that the ammonia in the laboratory is available as ammonium hydroxide, which is also a weak base. So, that can also be available for the production of HO minus. So, if more amount of hydroxide ions are there, so the side reaction for all these reactions, for all these complexation reaction can be the precipitation of cobalt hydroxide, but which we should avoid. So, precipitation of this hydroxide, and in fact, also sometimes the removal of these hydroxides, how we can manipulate this, that we will see afterwards. That what is the corresponding product if we simply use ammonium hydroxide instead of some reaction where cobalt chloride is reacting with dilute ammonia. So, this is there. So, 1 is coming. So, your difference is there 3, difference is 2, and the difference is 1, and this is also changing. Now, you have 4 of them, the cobalt nitrogen bonds, and 2 of them are cobalt chlorine bonds. So, this quartz sphere and all these things are changing. Then the fourth one, what we will just discuss in our next class, that how we can go for the next one is the color is different. This is green, but all other things are same. That means, is corresponding formula, this reactivity with silver chloride, and its the corresponding conductivity measurements that I will see afterwards in the next class, that how your the corresponding solution electrical conductivity, how it can also detect the presence of chlorides corresponding to the quartz sphere. So, what we see that the last 2 compounds having the same molecular formula, but the colors are different. That means, what we should guess, and the type of the electrolyte is also same, is 1:1 electrolyte, and second one is also 1:1 electrolyte. Only possibility is that you have 4 ammonium groups, and there are also 4 ammonia groups and the chlorides. So, what is the corresponding geometry? Until and unless we define this as the corresponding coordination number, what is the typical coordination number we call, and how the different number of these groups can be assembled around all these, this we will find it out. Then the corresponding positioning of these 2 groups. So, if we can have 2 different positions for the placement of these chlorides along with these ammonia groups, also we will find that this will be responsible for one typical coloration, and the second one is also responsible another different coloration. But the nature of this electrolyte type is same, but their corresponding positions will tell us something which is or another type of thing which we will consider in terms of the corresponding isomerism. Okay. So, everything we will see again in our next class. Thank you very much.